The definition of the determinant of a square matrix could look overwhelming at first sight. One reason is that the intuition behind the definition is not entirely clear without some explanation. If you're interested in knowing one way of arriving at the definition of the determinant, I have a series of videos for that, and I encourage you to check them out. Otherwise, you could keep watching this video and go to those videos later. So given an n by n matrix A, the determinant of A, and is denoted by that of A, is defined to be the sum of -1 to the number of inversions of sigma times A1 sigma 1, A2 sigma 2, and so on up to an sigma n, where sigma ranges through all the permutations of 1 up to n. And here Aij denotes the entry in row I and column j of A. Now, this is a gigantic sum, and there are n factorial terms in it, because each term depends on a permutation in Sn. And each term here is a product of n entries of A. Now notice that we're picking exactly one entry from each row and one entry from each column. And this power here is either 1 or -1, depending on the parity of the number of inversions. So we don't really need to know exactly the number of inversions. We just need to know whether it is odd or even. If it's even, then this is just 1, and if it's odd, then this is -1. There's a piece of notation regarding determinant that is worth knowing. If you have a matrix A whose entries are written out explicitly like this, then you can write the determinant of A as the entries of the matrix enclosed within vertical bars, instead of writing the determinant of this matrix. This way of writing the determinant can help save a lot of handwriting. Recall that the determinant of an n by n matrix A is given by this expression here. So suppose that my matrix is A, B, C, and D. Now this sum is over all the elements of Sn. So let me first just list all the permutations in S2. So the first one is the identity permutation, and the second one is this. Now we also need the number of inversions. The number of inversions of sigma 1 will be 0, and the number of inversions of sigma 2 will be 1. So the determinant of A is going to be given by this. And now we just plug in all the values. So I have -1 to the 0. And A1 sigma 1, 1 is simply A1, 1. And that's A. And here is A2, 2. So that's D. And then plus -1 to the number of inversions of sigma 2. So this is actually sigma 2 here. This is just 1. And A1, well, sigma 2 of 1 is 2. So this is A1, 2. And that's B. And here, this is A2, 1. So this is simply C. And simplifying, I get AD minus BC. Now let's look at a 3 by 3 matrix. Now there are 6 permutations in S3, and let me list all of them. Now let's find out the number of inversions of each of these permutations. So the identity permutation has no inversion. Now if you look at this, 2, 3 is an inversion, and that's all. In sigma 3, the only inversion comes from the pair 1, 2. And in sigma 4, I'm going to get 2 inversions, 1, 3 and 2, 3. And for sigma 5, I also get 2 inversions, is 1, 2 and 1, 3. And for sigma 6, I have 3 inversions, 1, 2, 1, 3 and 2, 3. Once you have these, you can figure out what determinant of A is using this formula here. And I'm just going to write down the result. So the determinant of this 3 by 3 matrix is given by this. And if you plug in all the values, you'll get the following. But there's actually a neat way of remembering how to compute the determinant of a 3 by 3 matrix. And what you do is as follows. You copy these first 2 columns and put them to the right of the matrix. Now what you do is you go down this diagonal. and take the product of the entries on this diagonal. So you get P1 times Q2 times R3, and then the second one will be P2 times Q3 times R1, and the third one will be P3 times Q1 times R2. Now for all these products, the sign is going to be positive. And you can see that the first term here corresponds to the diagonal here, P1, Q2, R3. And this one here corresponds to the second diagonal here. And this one here corresponds to the third diagonal up here. Now, what you do is you want to subtract 3 terms. And the terms are obtained from taking the product along these green diagonals. So this first green diagonal here is going to correspond to this term. The second green diagonal here is going to correspond to this term. And this third green diagonal here is going to correspond to this term. So there you go. Unfortunately, if you try to do something like this for 4x4 matrices or higher dimensional matrices, you will not get a determinant.